In 1989, the Exxon Valdez oil tanker ran aground in Alaska's Prince William Sound. 11 million gallons of crude oil contaminated nearly 2,000 kilometers of shoreline, tremendously impacting the surrounding wildlife. Despite Exxon's cleanup efforts, the spill had long-term consequences on the ecosystem, and its recovery will need to be studied for decades to come. Dr. Rob Campbell is a biological oceanographer for the Prince William Sound Science Center, and he has been monitoring the effects of the oil spill on the local environment for the past 15 years. He currently utilizes a Wet Labs Thetis profiler equipped with a wide variety of sensors to track the plankton population, water metrics, and nutrient levels of a vertical water column within the sound. The profiler is powered by a battery which allows around 6 weeks of daily profiles, but battery degradation has reduced the operating duration to a mere 3 weeks, and service and repairs are not feasible because the profiler is no longer supported by the OEM. Recharging the profiler takes a full day of work and prevents him from completing his other duties. To this end, he's requested the development of a new profiler that should improve on all aspects of the previous design. At Georgia Tech, Dr. Michael West has overseen engineering design teams working towards creating the replacement profiler. Previous teams' work include improving the profiler's hydrodynamics and upgrading data communication capabilities. Our team, the Prince William Sound Profilers, is committed to designing the new and improved profiler. We are Lauren Zoe, Peter Wilson, Lucas Ray, Zee Wee, Ben Goss, and Rachel Wallace. Dr. Campbell has determined that the main power draw is the motorized winch system that hauls the profiler up and down the water column. Playing to the strengths of our interdisciplinary team of mechanical and electrical engineers, the Prince William Sound Profilers have focused on designing an improved, more efficient subsea winch to boost the profiler's operational lifetime. Beyond reducing power consumption, other problems with the current profiler could be alleviated by our new winch design. The current winch is limited to holding enough tether to allow the profiler to explore down to a 100-meter depth, and Dr. Campbell would like to increase profiling capabilities to 200 meters. The current winch also has an ineffective braking mechanism that is easily overcome by the force of the waves when the profiler is parked at the surface for data transmission. Additionally, the current winch unspools at a constant RPM, causing the profiler to travel at varying velocities depending on the changing spool diameter. This interferes with the accuracy of its plankton identification software. Based off its plankton camera's resolution and sampling frequency, the new winch must be able to maintain a constant 30 cm per second upward velocity. Finally, because the winch will be operating in subsea saltwater conditions, it must be capable of working in the corrosive environment and be resistant to fouling. With regards to the entire winch redesign, the team prioritized ease of service and replaceability when choosing components and selecting materials to maximize the longevity of our winch. Based off the feedback from our advisors, we decided on a completely submersible model. This design utilizes non-corrosive materials like Delrin plastic and anodized 6061 aluminum to avoid the need for pressure vessels, and includes easily sourced replacement components. Within the winch, there are 5 major subsystems. The motor powers the winch and drives the gear train. The gear train reduces the motor RPM to turn the spool, then further reduces the RPM to turn the level wind, which guides the tether evenly onto the spool. Additionally, a brake system is included to prevent unwanted slippage of the tether. The motor that we decided to use as the mechanical power source for the winch is the Blue Robotics ROV thruster motor. Made for subsea applications, it avoids the need for a pressure vessel and has more than enough power to drive the winch. It is controlled by an open-source VESC motor controller and a Raspberry Pi. The gear train for the winch was developed in conjunction with the motor. We parameterized both components to find the optimal design to hold 250 meters of tether, run at an efficient motor RPM, and achieve the necessary gear reduction in torque. The winch system had a 40 by 35 by 20 centimeter footprint and fits comfortably within the previous team's hydrofoil design at the bottom of the profiler. This positioning ensures that the center of mass remains as low as possible to maintain the profiler's upright orientation in the water. With regards to tether material, we selected Spectra fiber rope, which has high strength and low elasticity. To mitigate tangling and improve the reliability of the system, we designed a level wind that will distribute the rope evenly onto the spool. The braking system, controlled by a waterproofed electromagnet, uses a parking pawl to allow freedom of motion in the reeling direction and has a neutrally active fail-safe design to improve braking and reduce power consumption. The level wind axle and chassis will be manufactured from aluminum, while the gears, spool, mounting components, and other level wind components will be manufactured from Delrin. In order to validate the design of the parking pawl during nominal operating conditions, a static 2D finite element analysis was performed. The pawl was subjected to a distributed compressive load derived from a 90 Newton buoyant force caused by the profiler and was stabilized by a roller constraint on the top back face. The FEA showed that the maximum von Mises stress concentration of 3.2 megapascals occurred along the bottom edge of the pawl, which is only 4.2% of Delrin's yield strength. Although FEA results should never be taken at face value without physical testing, the magnitude of the difference provides us the confidence that the pawl will not fail under braking loads. To examine how our winch design meets the design requirements, we've determined that it exceeds target specifications. Following energy calculations, we find that our improved design is capable of increasing the amount of profiles per charge from 45 to 175. Our spool is capable of holding the 250 meters of tether, and the pawl brake prevents slippage. Without access to the profiler's pressure sensor, we were not able to develop or validate a mechanism to maintain a 30 cm per second ascent velocity, but with our motor controller and onboard encoder, it is a feasible task for a future team to implement. Our material selection also makes our winch resistant to the subsea environment. For ease of service, our winch is easily maintainable with open source control electronics and parts from common vendors. With our new winch, the profiler will collect data more accurately and efficiently, and will now only need to be serviced once every 3 months compared to its current need of once every 3 weeks. The cost estimate for our winch is $25,000, where a custom subsea winch designed by an established manufacturer was quoted to be $50,000. At this time, we recognize that there is still more work to be done surrounding the winch. Future teams will need to integrate the winch control electronics with the necessary sensor interfaces to create the final electrical system. The winch will also need to be mounted and tested at 100+ meter depths to fine-tune the controller and identify other unexpected issues. Finally, we would like to give special thanks to Dr. Campbell, Dr. West, Dr. Jarawala, and Dr. Smith for their mentorship and support. With our team's contribution, this new profiling vehicle will allow scientists to continue monitoring the incredible ecosystem of the Prince William Sound.